So do you want to ask anything what we did in the last class actually? So in the last class we were talking about some fundamental means the relations and we were here actually we were talking about momentum equations uh, in in integral form actually based on the Reynolds transport theorem, right? So in that case, if you want to write the linear momentum part, so we were talking here, the rate of change of linear momentum would be equal to the applied force. So it's called the momentum balance. And based on Reynolds transport theorem, there actually we wrote here dN upon dt of the system can be mentioned here del over del t over the control volume eta rho into dB plus over the control surface eta rho b dot dA, right? So if you want to change that the Reynolds transport theorem for actually for linear momentum, so in that case your eta is getting changed by velocity vector and your n is capital N is changing by your p actually, that is your linear momentum, right? Correct?
Yes, sir.
Hello? So we were here in the last class. Now, from here, you can say that this dP upon dt, you can write in terms of force. And this force is practically your total force actually. So the total force on, you can say on any particular body or system uh, can be, what forces can it bear actually? So if I want to write here, so forces can be, let me draw the picture here because we were talking in the last class. So let's say this is your control volume. Now in this case, you have the 6 surfaces, right? The left side, right side, your front, your back, your top and bottom, right? So any particular, you can say the rectilinear shape would have the 6 surfaces. In this case, so all surfaces can also have the forces. This can be maybe a expansive force or maybe a contraction force. Okay, or maybe they could be parallel to the surface or they could be perpendicular to the surface. So if you want to draw the direction here, so in this case, if you want to draw the direction, so let's say this is the one of the part you have. So this is the part actually you have to always understand that what is happening where the force are applied or not. So let's say this. So you can apply a force maybe at this side, this perpendicular to this. Is it visible to you?
Yes, sir.
Right now you can change this maybe in a different side. Maybe you can apply a force in a reverse side, maybe this side. This is one of the way. So this force will provide a compressive force. This is for provide the expansive force. So compressive force normal to the surface will give you your pressure actually, right? And this would give you the volume, the dilation, the expansion part. This will try to expand it, so it will actually give your stretching. Okay. Now you can change maybe the another side also, that you can apply a force maybe let's say that parallel to the surface. Okay, so parallel means it could be either of the side. It could be in X side, it could be in Y side, it could be in any side, but parallel to the your surface. So this particular force will provide again your shear forces actually, right? So these are the only forces which you can apply only on the surfaces. Fine. So you will have the surface force. So surface force would take care everything, your tangential or your the normal forces both. All will come in the category of the surface force. Now, for body force is practically, you can say, uh, so body force practically you can say this always act if the weight of the body or your let's say your control volume itself, it always act downwards. The net body force will always act the downwards, no matter what orientation of your object is. It's always act at the center of the gravity of the system. It always act vertically downward. Now, depending on the direction coordinates, let's say you have taken, let's say this is for time being, this is your x coordinate. So if this is your x coordinates, so in this case, if you say the body force Fbx, let's say this is your x direction, so body force component in this case Fbx would be zero because the no body force is going there because that is the Fb multiplied by cos theta would give you the corresponding component in direction x. So you can write your force because most of the time when we solve the problem, we talk about x, y, z, three-dimensional figure. Or if you want to, let's say you have tilted this particular object, this could also be possible. You can tilt this object here and let's say now this your x direction would be or something like this. You can change this here, or let's say this is your x direction, and you can have another one maybe let's say the y direction could be let's say somewhere here. Now in this case you will have a body weight component in x direction also in your, let's say this is your y direction, because you have this is your main body force and multiply by corresponding theta will give you the sum component in x, y, z direction. Is that fine? So you can always mean that right here this force, this was the equation for your total force. Now you can do the force balances in individual the direction. In direction x if you are putting, so here you are putting the subscript x here, fxx, fbx, and this is here you have changed the x direction component of the velocity u here. The velocity vector here is got changed by u because the u it would be the velocity component direction x. Same thing you can write for y direction. So here it become y, here also it become y, and this here has come y direction velocity component. Same thing for z direction. So in chemical engineering operation actually, so these are the only two forces which we always consider. It could have either the surface force or body force. It means the electrical forces, nuclear forces, and all other forces we are not considering that because the magnitude of those in our operations are the negligible. Okay.
Yes, sir.
Hello. So
Yes, sir.
in that way, you can write your force balances in the x direction, y direction. Your main equation was this. Now you can write again the something is called energy balance for that. So in that case of the energy balance, you are just putting a pressure energy, then you want to write a kinetic energy, then you write a potential energy. So this is the special case of, you can say, some sort of the energy balance. Total energy would be the different. So this is one. Then so these are the constraints for that. You are talking about steady flow, no friction, and flow along a the streamline, incompressible flow. Derivation of this can be given, but that is not our part here for this course. Now, if you this in again, so this was the previous one. So here you have just changed the rectilinear one. So you have just put here x, y, z. Previously, we have put a v vector there. So vector b or either you put v vector x, y, z. The meanings are same actually. Now, let's say you want here a accelerating control volume. The control volume which you have, that itself is also mean the rotating or the moving with some constant acceleration. So in that case, your the left hand side only would change. You have the surface force, you have the body force, and this is the control volume which is also moving with some means acceleration. So practically, your this is the mass rho into dv and acceleration part. So this would be also considered here, and that the right hand side would be no change here. So these you would need when you will do the balances here. Now, in case of the angular momentum, so rate of change of the angular momentum, you are calculating from here. This actually the torque here. So here you are calculating the torque, and now here this you are the torque is practically is being calculated R cross V actually. So here this eta term is R cross V and rest of the part is same. So and now this total torque can come by how many ways? One is by surface force. So surface force would also give the torque, which will try to mean the rotate it. Now the gravitational is body weight would also give the torque if your body is not aligned along the direction of the gravity actually. So if it is not aligned, it will also give the some sort of the torque, just like the previous picture. So if you see here, so in this case, this one, this one. So in this case, the body weight would also give the torque because the direction of the center of the gravity is not aligned either of the coordinate. In this case, this body weight would also give the some torque. It will try to rotate it also, right? So this body weight can also give your torque component here. So that's what you have. This one here, so this is the torque given by body weight. Now you can also rotate the entire control volume actually. So this is the torque created by some sort of the shaft, because you can connect that control volume with some shaft or with some motor. That will also give the torque. So that would be the total torque actually by all means. Mean the again, we are not means considering the torque created by means other forces, electrical forces, magnetic forces, right? We are only considering the physical forces here only. So that can be applied only on the surface or only by body weights actually. Right hand side component would be same. So here there would be no change here. So that way you will do your torque balance or the angular momentum principle. Now you have the thermodynamics. So this is thermodynamics here. That's internal total change in the energy of the system can be calculated. The Q minus the W actually. Q is the heat supplied, and W is practically here. This practically the minus is the work done by the system only. So if it is work done by the system, this is plus by default. On the system, it will become the minus. So therefore, your energy would increase actually. So this would become Q plus W actually in that case. Now this you are the balancing here. Your eta term is getting changed by small e. So small e is the total energy per unit mass, and then you are the multiplying by differential mass, and this will give the total energy within that particular control volume. This is the total energy crossing influx from all the control surfaces if you have some inlet or outlet. So this would be the total means energy. Now total energy would have the how many components? That's what here. So this is your total energy here. You have here, this is U is the internal energy. This is coming from your pressure component, or you can say this total is coming from your, you can write some sort of your Bernoulli equation type of thing, right? Is it not?
Yes, sir.
So here, so Bernoulli equation, consider always your pressure energy, your kinetic energy and potential, and then you have added some your internal energy. So this would be the total energy of the system per unit mass, and then you this is your the nothing what is total mass actually. Velocity into A is mass, velocity into area would be the volume, and the ds upon dt of the system would be q dot by t, and now total entropy of the system can be calculated entropy within the control volume and total entropy coming from all the control surfaces. That would be the net change here of the surface. Now this is the entropy per unit mass again. So this small s is the property again, your per unit mass. Now then you can equate that inequality thing, and then you can balance it, and it will give you your feasibility of your process, just to understand whether this particular process is possible or not possible. Most of the time when we do all initial calculations in the undergraduate thing, we don't do all these calculations, right? Have you calculated this for the means any of the process? Hello? Can anyone hear? Is there anyone in the class or nobody there?
Hello? Yes, sir.
Have you calculated this thing for any of the process so far in your entire curriculum? Second law of thermodynamics, have you applied anywhere?
सर टोटल एंट्रोपी कैलकुलेट करी दोनों को अलग अलग तो याद नहीं कि कैलकुलेट किया
No, no. Have you applied the second law of thermodynamics for any process? ये छोड़ दीजिए. This part is, I am not talking. I am talking about the application of the second law of thermodynamics. Have you applied this for any of the process?
नो सर
Okay, but most of the time in case of CRE, you apply it just to check the reversibility or irreversibility, or whether that particular reaction is feasible or not, right? So that will calculate based on this entropy part here, the Q by A thing, and that's just to check the feasibility of the process, what type of the process is. Anyway, so that those were all your equations, all your fundamental equations that need to be applied in case of your integral control volume. integral form, you can write same equation in the differential form also. So that we will do one by one. So this is again a, you can write in short again that this was the Reynolds transport theorem. This is the correlation between intensive and extensive property. And here, if you want to write this again, you can say that if you want to write for mass, your capital M, N would change by capital M, eta would change by 1, linear momentum, N would change by P, eta would change by V vector. Angular momentum principle, this would change by capital H and eta would change by R cross V. In case of means energy balance, you can write total energy, this is the energy per unit mass. In case of entropy, you can write total means entropy and this is entropy per unit mass. So this part we did, and this is just again and this was the Reynolds transport theorem, which you have used to divide your the system approach into your control volume and control surface. And here this eta would change according to your this slide, and you can write all these fundamental laws actually. And based on that, you have to simplify that what is to be done or not, right? So this was here in case of this fundamental laws here. Now, this you have some physical significance of what the reverse transport theorem says. So this I already explained to you that N is your extensive property, eta is the intensive property, and this is things what coming from control surface, and this is from control volume, and this is the rate of change. So this physical interpretation is not the your part, but still you know what each term's meaning is. Then you are calculating rate here, that what rate things are exiting from control surface, control volume, and influx. This part we already covered. Now just write one problem statement, then we will apply all these laws one by one. Can you note down the problem statement? Hello?
Yes, sir.
So the problem is a liquid stream is flowing. A liquid stream is flowing into a tank at flow rate F naught in bracket meter cube per second with density rho naught in bracket kg per meter cube. Full stop. The tank is perfectly mixed and liquid is coming out at flow rate F in bracket meter cube per second with density rho in bracket meter cube per second. Apply the mass balance for this system. So you apply the mass balance for this system and let's see what are you getting.